Hi there. So today we're going to be looking at the particle dynamics in special relativity. So in the previous lectures, we've been looking at space-time, the geometry of space-time, and two important things that happen if we consider different reference frames. So that's time dilation and length contraction. Okay, but we haven't been looking at any particles being moving around. So that's what we're going to look at today. Now, before we get to that, I just want to make a little note on the use of space, time, distance, and proper time. So far, we've described the space-time metric, so the thing that we've been using to measure distances, by the following formula. So we had ds squared is equal to c squared dt squared minus dx squared minus dy squared minus dz squared. Okay, and we said this was just a slight variation on the Euclidean distance, but now we've got this minus sign over here. Okay, and then this ds, that just stood for distance, like you would use in Pythag. And then from that, we introduced the idea of proper time, okay, where we wrote d tau squared is equal to dt squared minus 1 over c squared dx squared plus dy squared plus dz squared. Yeah, and we said that was the proper time experienced by an observer moving through space-time, or in this case, proper time interval, since it's d tau. Yeah. Now, we used these two interchangeably, and I said if you want to measure the distance of a world line, you would use the space-time distance, and to actually do the calculation, we used this proper time formula. Now, all of that is correct. However, this ds over here, that has a precise definition. However, we were using it interchangeably. So to give the proper definition of the space-time interval, we're going to use ds squared is equal to minus c squared dt squared plus dx squared plus dy squared plus dz squared. Okay, so we're going to forget about this ds as being the like the Pythag distance, but using the Minkowski metric. And now instead, we're only going to be focusing on these last two equations over here. Okay, so notice the relative minus sign between the two. Okay, so this one in green, the d tau squared, that's still proper time. So this is our proper time interval. And ds squared, we're not going to be using that to describe the metric anymore. So ds squared from now on will be the space-time interval. Okay, so whenever we're going to be referring to the metric, we're going to be using g rather than ds squared. Okay, so ds squared is only reserved for the space-time interval from now on. Okay, and notice going from proper time to space-time interval, there's just a minus sign there. So just notice that we have d tau squared is equal to minus ds squared. Okay, so we've got the proper time d tau, proper time interval d tau, and the space-time interval ds. Okay, and if we ever need to refer to the metric, we're going to be using g. And just by the way, sometimes the metric is given by eta. So g is the more general metric. So g is the general metric. So we can use that for special relativity. However, it is general, so we can use it for more things like general relativity. Specifically for general relativity, you might see this referred to as eta. Okay. But it's exactly the same thing. It's just the special case of special relativity. We use this eta symbol instead of G, but it is exactly the same thing as we saw before. Okay, so with that out of the way, let's take a look at this space-time interval and what it does to space-time. So we'll see, depending on the sign of the space-time interval, so whether it's plus or minus, it splits up space-time into several parts. All right, okay. So the sign of s squared, so now we're looking at an actual length. Remember, ds was the interval. If we integrate that along the curve, we get the total length, in this case, s squared. So the sign of s squared separates space-time into several parts. Okay, so let's have a look at that. So we've got the following picture of space-time. We've got space along there and time along the vertical, or should I say c times time along the vertical, so everything has the right spatial units. However, in most cases, we're just going to say c is equal to 1 because it's just a constant, so we don't need to worry about it too much. Okay, but in that case, if c is equal to 1, we have the following diagonals here. One diagonal going this way, another diagonal going this way, in which the velocity or the gradient of this line is the speed of light. So v is equal to c. Okay, because we've got x along the horizontal, t along the vertical, the gradient would give us the velocity. Okay. And since we're working in units where the speed of light is 1, these two lines are at 45 degrees to the horizontal. Okay, gradient of 1. Now, this splits up our space-time. So we have these lines here going like that. We've got this portion over here. And we've got this portion over here. Okay, so this portion over here in this top part, this is where s squared is less than 0. We call this time-like. Okay, this green portion here, this is where s squared is greater than 0. We call it space-like. And lastly, these diagonal lines, okay, just the lines, the yellow lines there, this is where s squared is equal to 0, and we call this light-like. Okay, now those are just names. You don't need to worry too much about that. It's just based on the fact that this metric gives us our space-time distance s squared. If we look at that in this top and bottom portion in blue, we find that the sign is negative, and we just call it time-like. The green parts on left and right, we call that space-like, and that's where the sign is positive. And then the points along the two diagonals give us s squared is equal to 0. We call that light-like. Okay. And just a bit of terminology. If this was in a higher dimension, of course, we can't draw much on a 2D piece of paper since we're working with 4D space-time. However, if you imagine this in more than 2 dimensions, what we will get is the following. These diagonal lines, if we rotate them around into the other dimension, we end up with a cone like this. Okay, so this cone over here, let's just highlight that there. So we've got this cone going around. This is called the light cone. Okay, so hence the name light-like. Now, the reason we call it the light cone is, first of all, it makes the shape of a cone. And secondly, these paths along the diagonal are the paths of light through space-time. So light rays, or you can think of photons, move along this diagonal. Okay, so move along this diagonal here. Okay, so we can see that by looking at this metric where s squared is equal to 0 to see what actually happens there. So s squared is equal to, we can look here, it's minus c squared t squared, and then plus x squared plus y squared plus z squared. So minus c squared t squared plus x squared plus y squared plus z squared. Now we know that along the surface of this cone, we have s squared is equal to 0. Okay, that's just separating the space and space-like, time-like regions. However, we can take the c squared t squared to the other side. So we get x squared plus y squared plus z squared is equal to c squared t squared. We can divide through by t squared. So we get x over t squared plus y over t squared plus z over t squared is equal to c squared. Now x over t, y over t, z over t, that gives us x dot squared plus y dot squared plus z dot squared, and that is equal to c squared. Okay, now x dot squared plus y dot squared plus z dot squared, that's just the velocity squared, is equal to c squared. So v is equal to plus or minus c. So we see that the space velocities, or your standard velocities that you would measure, is equal to plus or minus c. And that corresponds to light moving either to the left or to the right in this diagram, but only along the diagonals. So light is forced to move at the speed of light. We'll see the reason for that later on, but for now we can just see that light moves along these light-like diagonals. In other words, they move on the surface of this light cone. Okay, and for velocities less than the speed of light, in other words, the velocities of massive particles, not massless particles, they move within the light cone. So we see here, we've got this light cone produced by the metric. Light will move along the surface here, and massive particles, they move within the light cone. Okay, they are restricted to move it within the light cone because they have mass. And just a note, nothing is outside this region. Okay, so the space-like region, there's nothing moving there, because if something were to move out here in this space-time region, it would have to have a velocity greater than the speed of light. Okay, and we can't have that. So nothing can move within this region. The fastest particles, or move at the speed of light, they move on the surface. All of the other massive particles, they are constrained to move within the light cone. Okay. Now, this light cone is made up of two parts. We've got this upper part and this lower part. This upper part we see is moving to larger time values. So we say that is future pointing. So anything that is moving through space-time must be moving towards the future. We don't have things traveling back in time. So if there's a particle, let's say over here, it must move within its light cone towards the future. So if we draw just a little mini light cone here, okay, it must be heading up something like that, again, within its own light cone, okay, towards its future. Okay, so that's just a quick little introduction to the particle dynamics. We have massive particles, they move within these light cones. The massless particles, like the light ray or the photon, they move on the surface. Nothing is outside the light cone, because if it were, its velocity would be greater than the speed of light, and we can't have that. Okay, so let's take a look at more on this idea of the velocities of particles. So far, when we talk about velocity, we mean the velocity as measured in just our 3 spatial dimensions. So we took x, y, z, we found x dot, y dot, z dot, and we calculated the velocity that way. Now that is just the velocity through space, right? Because we're only considering the spatial contributions. However, in space-time, there are 4 dimensions. So there should actually be 4 contributions to the so-called space-time velocity. Now, since there's these 4 contributions from the 4 dimensions, we usually call these 4 velocities. Okay, so 4 dimensions of space-time, 4 dimensions of the velocity. Okay, so let's have a look at that. So velocities in space-time. Okay, so before we get onto that, we just need to do a quick recap of moving from one coordinate system to another. Okay, so this will be important for when we look at alternative views of velocities in space-time. So previously, we saw that the Lorenz transformations we gave that the symbol capital lambda, so L for Lorenz, allowed us to go between moving and non-moving frames. Okay, and we saw that this was just a very special case of a coordinate transformation. So, in fact, this was a linear transformation. So if we were to go from, let's say, Cartesian to polar, that would be a non-linear transformation. However, in this case, if we're going from a non-moving frame to a moving frame, we could write this as a linear transformation of the coordinates. Now, since it was a linear transformation, we could write it using a matrix, right? Linear transformation, we can use linear algebra. So in fact, a space-time point in the primed coordinate system, so your coordinate system, if you're moving, is given by x0 prime, x1 prime is equal to, and then we had this nice equation, gamma minus beta gamma minus beta gamma gamma. So those were all the factors involved in the transformation, x0, x1. So we said this was a boost in the x direction. Okay, so we have the unprimed, for example, that's me stationary. If I want to move to your frame, which is moving, we need to use this Lorenz transformation, lambda. Okay, and that gives me the points that you would be measuring in your primed system. Okay, now a nice thing about these transformations is we can also view these linear transformations as hyperbolic rotations. Okay, so we can also view these transformations as hyperbolic rotations. Okay, emphasis on the hyperbolic part. It's not a usual Euclidean rotation. So hyperbolic rotation from one frame to another. Okay, and the way that we write it is very analogous to the usual rotations. However, these are now hyperbolic. So we have x0 prime, x1 prime is equal to hyperbolic cosine or cosh omega minus hyperbolic sine omega minus hyperbolic sine omega, and then hyperbolic cosine omega. Okay, x0, x1. Okay, so we call this transformation matrix a hyperbolic rotation, quite analogous to a standard rotation in which we had x prime, y prime is equal to cos theta, sine theta, minus sine theta, cos theta, acting on xy. So in red, we have the standard rotation by some angle theta, okay? So here, this is just a rotation from one frame, let's say xy, to another frame, x prime, y prime, where we have rotated by some angle theta. Now, in special relativity, we're working in Minkowski space, not Euclidean space. So what this corresponds to is not a standard rotation, hence hyperbolic rotation, but it's more like this. So we have x, y, sorry, not x, y, x and t, or should I say x1 and x0, and then we have something like this. x1 prime, x0 prime, sorry. My lines, there we go, something like that. Where we have x1 prime and x0 prime, something like this. So it's not your standard rotation, it's more like a squishing and stretching of the axes. Okay, so it's not just a rigid rotation of the axes. You see that things are getting squashed inside like this. Okay, you don't have to worry too much about the visuals. I will provide some links that explains this a bit more. But just keep in mind that it's not a rigid rotation of the axes. It's something more complicated. Okay, more like this picture that we have here. Okay. And instead of a standard angle theta, we use the so-called hyperbolic angle omega. Okay, so that's the hyperbolic angle. Okay, so if we look at these two representations, we've got the Lorenz transformation in terms of gammas and betas. We've also got the same Lorenz transformation in terms of this hyperbolic angle omega. So just by comparing these two, we see that this hyperbolic angle can be written in two ways. So if we look at the cosh term, we see that cosh omega is equal to gamma. And if we look at the hyperbolic sine term, we see this hyperbolic sine is related to minus beta gamma, but we know that gamma is cosh omega, so we can write that as hyperbolic tan omega is equal to beta. Okay, so just remember hyperbolic tan, that's hyperbolic sine over hyperbolic cosine. Okay, so we've got these two equations here. Let's say equation 1 and equation 2, relating our previously known quantities, the gamma and the beta, to our newly introduced quantity, the hyperbolic angle. Okay, so let's just highlight that's our new thing, omega. Okay, so equation 2 gives us the relationship between this hyperbolic angle omega and the previously known quantity, the standard velocity. Because remember, we have that tan of omega, hyperbolic tan of omega, hyperbolic tan of omega is equal to beta, but remember we defined that as V over C. So this gives us the relationship between this new thing that we called omega and the standard velocity that we know. Okay. Just as a bit of terminology, this hyperbolic angle omega is called the rapidity. So this is called the rapidity. Okay, just a bit of terminology, you might see it come up later. Now, you can either work with the velocity or you can work with the rapidity because we've got this one-to-one relationship between the two. However, we will see that working with the rapidity is much more intuitive than working with the velocity. Now that sounds a bit weird. Why wouldn't the standard velocity be intuitive? But remember, we're working in special relativity, and because of this mixing of space and time and the limit of the speed of light, things get pretty weird. So in fact, working with rapidity makes more sense. Okay, I'll give you the major reason why we work with rapidity more than the velocity, and that's because, let's give a big exclamation mark here, velocities do not add in special relativity. But rapidities do. Okay, so what do I mean by velocities do not add in special relativity? Well, to explain that, we just need to do a very quick little thought experiment, as Einstein would say. Imagine you're in a car. Let's draw a little car here. Okay, so you're in a car and it is stationary. Then you turn on your headlights and the light rays move off. Okay, they move off in front. Now, if you are stationary, you would say that these light rays move off at the speed of light. Of course they would. So the light rays move at the speed of light. No problem there. Now imagine if your car is moving. Okay, let's redraw the car. Okay, so now we've got some speed lines here. The car is moving at the speed v. Okay, and you, again, turn on your headlights. Now in standard Newtonian picture or pre-Einstein picture, we would say that these light rays are now moving at the speed v plus c, because the car is moving at a speed v, and then the light rays move off from the car at speed c. So if we're standing by and we're watching the situation, we would say that the light rays move at v plus c. But that can't be true, because the speed of light is the speed of light in every frame. Okay, so there's no special frame in which the speed of light is faster than c or the speed of light is slower than c. So this picture of simply adding the velocities is just wrong. Okay, so velocities do not add. Okay. In your notes, there is a little derivation of the true velocity addition formula. It's quite complicated. It doesn't look intuitive at all. Okay, you've got the velocities being added in the numerator, and then in the denominator, you have 1 plus the product of the velocities. It just seems very weird. Now, if we instead consider rapidities instead of velocities, we see that it makes much more sense. Okay, so let's have a look. So when I say rapidities add, I mean that if we have one rapidity and another rapidity, for example, your car moving has one rapidity, light has another, we can then simply add them. So the final rapidity is equal to omega-1 plus omega-2. Where omega-1 is the rapidity of the car. Now the light is moving away from the car. So according to us, it's moving at rapidity omega-1 plus omega-2. Okay, we just add the velocities because of the moving frame. Now, rapidities add. That's it. That's all we need to write. If we want to go back to the velocity picture, okay, like it has in your notes, we need to go from rapidities back to velocities. Well, that's easy to do. We've got this conversion formula here using hyperbolic tangents. So let's do that. So if we take the hyperbolic tangent on both sides, we get hyperbolic tangent of omega. That is the final velocity, because omega is the final rapidity, is equal to the hyperbolic tangent of omega-1 plus omega-2. Okay, now we want to write this in terms of velocities, so we need to use this addition identity for the hyperbolic tangent. So this is given by the hyperbolic tangent of omega-1 plus the hyperbolic tangent of omega-2 divided by 1 plus the hyperbolic tangent of omega-1 times the hyperbolic tangent of omega-2. Okay, so this gives us our conversion formula, if you want to think of it like that. Now, tan of omega, that is v over c. So think of that as your final velocity after addition. So v over c is equal to v1 over c plus v2 over c divided by 1 plus v1 over c times v2 over c. Now, if we multiply through by c, we're going to get v final is v1 plus v2 over 1 plus v1 v2 over c squared. And this is what you should see in your notes. However, this is not intuitive. Why would you add velocities in the numerator and then divide by this funny factor in the denominator? The only reason this looks unintuitive and complicated is because we're looking at it in the wrong way. We shouldn't be looking at velocities in terms of the spatial velocity v. In relativity, we should be looking at velocities in terms of rapidities. So we should be looking at this omega instead. You see, it makes much more sense because rapidities can just add. Whether you are adding the speed of light to the speed of your car, there's no problem with that. You simply add the rapidities. However, if you want to look at it in terms of the velocity picture, you see it's a bit more complicated. Yeah. So we should be working with rapidities rather. Okay, so I've got a bit of a homework problem. Number 1. Show that adding rapidities fixes the problem of moving faster than the speed of light. Okay, so just one question there for this section. So we've got this idea of rapidities. Omega 1 plus omega 2 is equal to omega. Please show that this actually fixes the problem of moving faster than the speed of light. So with your standard velocity addition, we could achieve velocities greater than the speed of light. Think about your moving car and then turning on your headlights. Show that if we look at it in terms of rapidities, we can never be moving faster than the speed of light. Okay, so please show that. Okay, if you do have any problems with this homework question, please just let me know on the WhatsApp group. I can help you out with some hints or clues or something like that. Okay, so this is just another way of looking at your spatial velocity. So your v being a vector composed of x dot, y dot, and z dot. However, that is still looking at only 3 dimensions, right? This is what we would see every day. However, if we want to look at a proper space-time view of everything, we need to be looking at the 4 velocity. Okay, we can't just consider parts of it. We need to look at the whole thing. Okay, so let's take a look at that. Okay, so space-time velocity rather than just space velocity. Okay, and like I said before, since this is including all 4 dimensions of space, we usually call this the 4 velocity, as opposed to the 3 velocity, which we have been considering up to now. Okay, so before we go on to velocity, we need to talk about position, because from position, we get to velocity, and then acceleration and so on. So a point in space-time is given by x, and if we use our notation of x0, x1, x2, and x3, we can write this as x0, x1, x2, x3. This is our location in 4-dimensional space-time. In other words, the position and the time. And again, as measured by you, or in your reference frame, or your chosen coordinate system. If you were using another coordinate system or another reference frame, these numbers would then be different. Okay, so please keep that in mind. As soon as you write down numbers, you are assuming a coordinate system. However, this x over here, this is independent of coordinate system. The point in space-time doesn't care what system you use. It's just a point in space-time. But to get the components, you have chosen a coordinate system. Okay, please don't forget that. So what we would like to do now is use this idea of position in space-time to then come up with velocity in space-time. Now, we've already discussed that this position quantity is invariant under coordinate transformation. Okay, so points in space-time, doesn't care what how you label it. So from this invariant, we would like to create a velocity invariant. In other words, a velocity that also doesn't care about coordinate system. Now, we know that proper time, tau, is an invariant. You should have shown that in the homework exercise. So we can use that invariant, the proper time, along with this invariant, the position, to create another invariant, which we call the for velocity. So what we do is we define the for velocity u. Okay, that's usually the notation given to the for velocity. We define it as dx. So let's rewrite that. dx by d tau. Okay, that's just the definition. It's a good definition because x, that is invariant, tau, that is invariant. So this for velocity is also invariant, which is what we need. So if we write this out in component form, we can write this as dx0 by d tau, dx1 by d tau, dx2 by d tau, and dx3 by d tau. Okay, good. Now, remember that x0 is just another way of writing c times t. And also, using our time dilation formula that we came up with, we know that d tau is given by 1 over gamma dt. Okay, that was our time dilation formula. So we can substitute that in. We're going to end up with gamma c dt by dt. Then we're going to have gamma dx by dt, gamma dy by dt, and gamma dz by dt. Okay, that's just going from proper time to coordinate time. So for the first entry, dt by dt, that's just 1. So we end up with gamma c. Next, we end up with gamma x dot, gamma y dot, gamma z dot. Now we've got gammas throughout. We can treat this like a vector and take the gamma outside. So we can write this as gamma c comma x dot y dot z dot. Now x dot y dot z dot, that forms a 3 vector that we just call the velocity. So we could write this compactly as gamma c comma 3 vector v. So this is just a 3 vector x dot y dot z dot. Okay, we've got a little compact notation there. So this is the for vector for the for velocity. Okay, so we've got another homework question now. Calculate the magnitude of this for velocity. Okay, so it's a vector. We can calculate the length of the vector. I'll give you a little hint. So hint. Remember that the metric, we originally used the metric to calculate the length of a curve. We can also use the metric to calculate the length of a vector. So if you want to calculate the length of a vector squared, this is given by GAB, VA, VB, where VA and VB, those are the vector components, and G is the metric. Remember that we use the Einstein summation convention. Okay, so just to reiterate, if you've got an index up and an index down, you sum over the possible values of that index. So we've got an A up and an A down. We sum over the possible values of A. We've got B up and B down. we sum over the possible values of B. Okay, so using this formula, please calculate the magnitude of this 4 vector. Okay, so that's part 1. And then part 2. What does this tell us about your speed through space-time? Not your speed through space, but your speed through space-time. So what does this value tell us about your speed through space-time? Okay, so after question 1, you should get a nice result, and then please tell me the physical consequences of that result. Okay, that's part 2. Then part 3. So use the fact that GAB, UA, UB is equal to a constant. Okay, so the length of the vector is a constant, of course. You just need to find what that constant is using question 1. Okay, so I don't want to spoil it, so I'm just going to say it's a constant. So use the fact that the length of the velocity vector is a constant to calculate the 4 acceleration. Okay. Now, just recall from the position to the 4 velocity, we had d by d tau. That's how we got the 4 velocity. The 4 acceleration will be quite similar. So it's analogous. A is equal to du by d tau. Okay, so use that to calculate your 4 acceleration. Okay, and you can start from this formula over here. Okay, so that's part 3. Part 4. What is the angle between these 2 vectors? So the angle between U and A. So we've got a 4 vector U, a 4 vector A. What is the angle between them? And last question, question 5. Draw a sketch of a massive particle world line including the vectors U and A. Okay, now, of course, you can't draw this in many dimensions. So just draw it with X along the horizontal, T along the vertical. Okay, so a 2-dimensional space-time. Okay, and please include the vectors U and A in that picture. Okay, so that is the definition of the 4 velocity, and then this 4 acceleration that's left as homework. Okay, next, after we've discussed velocity and acceleration, the next thing in the usual classical mechanics is to look at the 4 momentum. Well, sorry, in normal classical mechanics, you would talk about momentum, like in first year, but now we're going to be looking at 4 momentum. Okay, the space-time analog of it. Okay, so we can now define the 4 momentum. Okay, so how do we go about defining the force momentum? Well, we've already looked at the force velocity, okay, u. Now, in first year, you looked at the force velocity, sorry, not the force velocity, you looked at normal velocity, you multiplied it by mass, and you got the force momentum. We can do a similar thing here. We can define the force momentum P to be equal to the mass of the particle m times the force velocity u. Okay, so that's just one way of defining it. Another way of defining it is P is equal to, we can write it in terms of components. It's going to be E over C, and then we have Px, Py, and Pz. In other words, it's going to be E over C and the 3 momentum vector P. Okay, so we've got 4 components. It's a bit weird that the first component is the energy. So we see that the first component of the force momentum is the energy. You might be thinking, how did we get that? Okay, so that's not too obvious from the first expression where we use the force velocity. However, we do need to figure out why it's there. Okay, so we've got force momentum defined in terms of force velocity and the force momentum defined in terms of energy and 3 momentum. Okay, so the way we explain this energy here is using the idea of the action. So the action is an invariant scalar that holds all the information about the particle's dynamics. Okay, so you'll learn more about the action later, but it's just a way of containing all the particle dynamic information in one scalar. So the way that we define the action for a massive particle in special relativity is given by capital S for the action is minus m times c, the integral of our space-time interval ds. Yeah, this is just the definition of the action. Now, from the action, we can then find several things. Most importantly, with the action, we can calculate the energy and we can calculate the momentum. So from this, we can calculate the energy as minus ds by dt. We can calculate the momentum in the various directions as well as ds by dx, py is ds by dy, and pz is equal to ds by dz. Okay. Now, if we just took all 4 of these and wrote it as one thing, which is typical in special relativity, we like to combine space and time, we get the following. We get minus ds by dt, ds by dx, ds by dy, ds by dz. Okay, we've got this so-called space-time gradient of the action. So if I just highlight that here, we've got minus d by dt, d by dx, d by dy, and d by dz. Okay, so like the gradient that you would see in Math 212, remember the del is d by dx, d by dy, d by dz. In special relativity, we've got this extra term here, d by dt. However, we just add it all together because that's how we combine space and time. And we see that all of them just act on S. Okay, and then this gives us, if we just define this to be the 4 momentum, capital P, okay, right, we just put all the components together, we see why this first term here is E over C. Of course, we need to now divide by C to make sure all of the units are correct. So we want all spatial units, so we divide by C. Okay, and then this gives us the reason why the first term is the energy. Okay, it's derived from the action and its derivatives. So we get here E over C, Px, Py, Pz. And that's our 4 momentum P. Okay, so that's quite similar to working with the 4 velocity. Now we've got it in vector form. We would like to now work out the magnitude of this vector. Okay, what is the length or the magnitude of this 4 momentum? Okay, right, we do it very similar to how we do it for the 4 velocity, or should I say how you'll do it for your homework. We have that the magnitude of P squared is given by GAB, PA, PB. Okay, and we know the metric, that's just the plus, minus, minus, minus. Okay, so what we have here is that the magnitude of P squared is given by, E squared over C squared. So that's just your first component squared, E squared over C squared. And then we have minus Px squared minus Py squared minus Pz squared. Now, all of that we can just combine into P squared. So we're going to have that the magnitude of P squared is given by E squared over C squared minus P squared. Okay, that's fine. That gives us the length of the vector. However, remember back at the beginning, we gave this alternate definition. So the first one is like your first year definition with mass times velocity. The second variation here is derived from the action. Now they're the same vector, so they should have the same length. So let's take a look at the length of the P vector using this first definition, the m times 4 velocity. Okay, so spoiler for your homework, but the length of P squared in terms of your 4 velocity will be m squared times the length of u squared. You'll see in your homework, it's a good thing to go through the calculation anyway, but this is going to be m squared c squared. Okay, so little spoiler on that. Now we've got these 2 views on the 4 momentum. We've got that one and this one. Now they must be the same, right? So if we equate the 2, we end up with E squared over C squared minus P squared is equal to M squared C squared. Okay, we can take the P squared across, multiply through by C squared, and we end up with E squared is equal to M squared C to the 4 plus P squared C squared. And this is the energy momentum relation or the energy momentum dispersion relation. Okay, depending on what you're looking at, you might hear different names for this. Okay, so this is the energy momentum relation. Now we can look at a couple special cases of this. Okay, just to get a feeling for how to work with this expression. So firstly, let's say that the particle is not moving. So stationary particle. So if the particle is stationary, it has no momentum. It has no 3 momentum, should I say. So P is equal to 0. So this implies that E squared is equal to m squared c to the 4, or we can take the square root. We get E is equal to mc squared, right? The famous Einstein formula. So we see that this famous formula E equals mc squared is just a special case of the more general energy momentum relation. Okay, so what this says is that an object, a massive object, should I say, has energy even though it's not moving. And that energy comes from the fact that it has mass. So things with mass have energy, right? They are the same. If we just get rid of the c squared, right, or we say c is equal to 1, we see that energy is just equal to mass. They are the same thing. Okay. And next, what happens if the mass is 0? So for a massless particle. Okay, so this is just another special case. If the mass is 0, the particle still has energy. But now, since the mass is 0, we have E squared is equal to P squared C squared. Again, taking the square root, we get E is equal to P times C. And you should have seen this when you looked at photons. This is the energy of a photon. Okay, but it's not just a photon, it's any theoretical massless particle would have this energy momentum relation, E equals P times C. So we see that for a photon or a massless particle, the energy is linear with respect to momentum. It's P times C. For a non-relativistic, first year kind of particle, we saw that E is equal to P squared over 2m. Okay, if it has mass, we can of course divide by the mass because it's non-zero. So we got this in first year, E equals P squared over C squared. We've got this quadratic behavior in P. However, if it's massless, we've got this linear behavior in P. Okay, so certain interesting things can come from that. Okay, so just keep that in mind. Massless particles, they are different, okay, because of their energy momentum relation. However, this total relationship here, this over here in green, the E squared equals m squared c to the 4 plus p squared c squared, that equation, that works with anything, right? Stationary particles, massive particles, massless particles, moving particles, it covers everything. So everything else is just a special case of that formula there. In fact, we can also see that the non-relativistic energy equation is also a special case of that. Okay, so that will be the last thing for today. So looking at the non-relativistic limits. Relativistic limits. Okay, so there's two ways to look at this non-relativistic limit. Both ways are mathematically the same, but however you want to think about it. Either we can say that v is much less than the speed of light. Okay, so you've got some velocity that is much less than the speed of light, which in everyday situations is true, right? Your fastest car or fastest jet, that's nowhere close to the speed of light. Okay, so you can either look at it like that, or if you want to look at it in a different way, you can also think of it as the limit as c goes to infinity. In other words, if you imagine that light propagates instantaneously. Okay. So either you can think of the velocity being much less than the speed of light, or you can think of it as light moving instantaneously. Okay. Either way, you get the same limit. So we're going to use this idea along with our energy momentum relation to recover the non-relativistic limit. Okay, in other words, your first year formulae. So we start. E squared is equal to m squared c to the 4 plus p squared c squared. Okay, the first thing we do is factor out m squared c to the m squared c to the 4. So we have e squared is equal to m squared c to the 4, 1 plus p squared c squared over m squared c to the 4. Okay, so we just factored that out. Okay, next we can take the root, okay, to solve for e. So we have e is equal to the square root of m squared c to the 4, 1 plus, and then we have p squared over m squared c squared, like that. Okay, now remember that in this case, c is very, very large, or you can think of it as the momentum p being very small. Either way, this term over here is very small. So you can either think of it as p being much less than the speed of light, because the velocity is much less than the speed of light, or you can say that c is going to infinity. Either way, that term is very small. Okay, so what we're going to do now is take the square root. So we have e is equal to mc squared, and then we have the square root of 1 plus p squared over m squared c squared. Okay, something like that. Now, p squared, we can write that as m times v, okay, because that's what momentum is. So we have mc squared, square root of 1 plus m squared v squared over m squared c squared. Okay, now the m's will cancel, and we end up with e is equal to m squared c squared, the square root of 1 plus v squared over c squared. Now we're going to do a little tangent from here. Okay, so little tangent. Notice this factor here, square root 1 plus v squared over c squared. Maybe I'll put this as another little homework problem. Write this in terms of the gammas. Write this in terms of gamma. Remember gamma from before, that factor that we used in time dilation and length contraction. It looks something like this. So try to rewrite this using gamma, see what you get. Okay, but that's a little tangent. Let's get back to our calculation. Okay, so what we want to do now is look at this root expression, but keeping in mind that this term v squared over c squared is very, very small. So we have m squared 1 plus v squared over c squared to the power 1/2, where this term is very small. So if it's very small, we can do either a Taylor expansion or binomial expansion, whatever you want to call it. But this expression here, 1 plus x to the 1/2, for x being very, very small, we can expand that out. In fact, we can expand it out as mc squared 1 plus 1/2 v squared over c squared plus some higher order terms. Okay, so we're not too worried about those higher order terms because they get smaller and smaller as you go up. So let's finally write this out. So we have mc squared plus 1/2 mv squared, that looks familiar, plus some higher order terms. Now this first term is just a constant. So this is a constant. And it is the rest mass energy, as we spoke about up here with this E equals mc squared. So when the particle is at rest, it still has energy given by E equals mc squared. Okay, so that appears in our series expansion here. Now, the reason this term doesn't matter in first year is because when we're looking at things in terms of energy, remember that we're only interested in energy differences. So if you want to work out the work done by a force, for example, using that work energy theorem, it is the change in kinetic energy or the change in potential energy and so on. So if we're looking at the changes in energy, adding a constant doesn't matter, because if we have E2 minus E1, for example, let's actually do it explicitly here. So E2 minus E1, let's write it as mc squared plus half mv1 squared mv2 squared minus mc squared minus half mv2 squared. We see that this mc squared is a constant. It just goes away. And we're left with the change in kinetic energy. So adding a constant to the energy doesn't affect anything. So we don't see it in first year because we looked at the changes in energy. However, it's still there. Okay, relativistically speaking, this rest mass energy is there, and we can't just neglect it. Now for the second term, that's also familiar to us. This is the kinetic energy, the standard half mv squared. And we see that taking our relativistic energy formula, this one over here, if we take the limits of small momenta or small velocities or infinite speed of light, however you want to think about it, we see that in that limit, we recover the classical, or should I say first year kinetic energy. So this is like our first year non-relativistic relativistic kinetic energy. Okay. And then the remaining terms in the series, you can add as many as you want to get more and more accuracy. Those are called relativistic corrections. So we've got the standard half mv squared that we know and love. However, if you want to express things relativistically, you either have to use the full relativistic energy formula, or you need to make corrections to this kinetic energy by adding those higher order terms. Okay, so last bit of homework for today. Find the next two terms in this series expansion. So we've got the first two, the rest mass energy and the standard kinetic energy. Please find the next two terms, in other words, the relativistic correction terms. Okay, so what are those terms? So if you're trying to approximate relativistic speeds or relativistic phenomena, you need to add these correction terms, or just use the full energy momentum equation. Okay, but depending on the situation, sometimes it's better to just add some correction terms. Okay, so that's it for today. Please go through these homework problems. They will be very important for the test coming up. Next time, we will take a look at certain phenomena that can only be explained using this relativity framework. So we're going to be looking at the muon paradox. Okay, I'll explain that later on, and how electricity and magnetism are connected using relativity. Okay, so I did go through this last semester at the end of your electricity and magnetism section, but now we're going to do it properly. Okay, with all of the calculations and all of the explaining. Okay, so how we combine electricity and magnetism into one phenomena explained using special relativity. Okay, as always, if you have any questions, please post them on the WhatsApp group. I will explain or help you out as soon as I can, or you can send me an email. I'll be happy to help you with that as well. Okay, but please do go through these homework problems, give them a go. If you're having trouble with the homework, please ask for help. Okay, so it's not like a test, right? You can ask for as much help as you want. I'll be happy to help you with that. Okay, but the solutions will be available at the end of the week. Okay, so I don't like giving the solutions now because it's very easy to just look at the solutions before attempting it. So you should struggle at least a little bit to try and do the homework before you see what the solutions are. Okay, but anyway, if you need help, please ask. Okay, so next time we will go through those relativistic phenomena. Okay, I'll see you then. Bye.